This is section 17.3, conservative vector fields. We just introduced vector fields in section 17.1 and mentioned the word conservative vector field at that time, but now we're really going to dive into it now that we have the ability to interact with them using line integrals from section 17.2. So the goals for this section are, first we need to figure out what are simple curves and what's a simple closed curve. Then we also need to learn what kinds of regions there are, like connected or simply connected regions. Finally, we'll actually get into the meat of the topic, which is where we can tell whether a vector field is conservative or not, and then find its potential function. And then we actually get a new fundamental theorem. It's the fundamental theorem of line integrals. What you'll find through the rest of this chapter is that we're kind of like building more and more fundamental theorems of calculus. Yeah, it's pretty awesome. Okay, well, anyway, let's just jump into it. So first thing is the types of curves and regions. So you can either be a closed curve or not a closed curve. And you can be a simple curve or you can be not simple. And instead of writing down the definition in this case, I'm just going to give you a little like sketch of all the different possibilities, because there's 4 possibilities here. So this is curves. A simple curve doesn't cross itself, and a closed curve comes back to where it started. So like a simple closed curve would be a curve that it doesn't ever cross itself and it comes back to where it was. If it's a non-simple closed curve, that means it comes back to where it started, but it maybe like crosses itself on the way. Not closed just means it doesn't come back to itself. So a simple not closed curve would be like this, and a non-simple non-closed curve is like the worst case scenario where it doesn't start and end in the same place and it also crosses itself. The facts of the rest of our chapter will often depend on simple closed curves. Sometimes it also depends on certain kinds of regions. So let's get some different kinds of regions. Your region could be connected or not, and it could be simply connected or not. Nah, I'm just going to say you can either be not connected, you can be connected. I don't have room if I do it like that. So you could be connected or not. And you could be simply connected or not. And simply connected is all one adjective. It's not like you can be simple. You'll see. Okay. So what are these different kinds of regions? Well, a connected region just means it's in one piece. So if you're not connected, like if you're just completely disconnected, then your region might just be 2 regions. If you're simply connected, then you are connected. So there's nothing that goes here. This never happens. Connected and simply connected means that you have a region and it's all one piece, and there's no holes in it. So this is a simply connected region. If you're connected but not simply connected, it means that there's one piece, but there's maybe some holes poked in it. This region does not count as simply connected, even though it is connected. So these are just some vocabulary words. It will turn out that the theorems we're using depend on some of these vocabulary words, and I'm going to use them, and then they're not actually going to come up that often, but we should know what the words mean in the theorems that we're talking about. Okay. Yeah, so if you try to write down definitions of this, you can do that. If you have a curve C and it's written parametrically, then it's a simple curve if it never hits itself. So that means if you pick 2 different times, then you end up at 2 different places. And then the curve is closed if you start and end at the same place. So these are our definitions of simple curve and closed curve. I don't think we're going to try to write down definitions of connected and simply connected. We're just going to use these pictures. And if you take higher level math classes, you'll get to dive into those definitions and like why we care about them. The field of topology is really interesting, and you should ask your instructor about it sometime. I don't know. This is getting into topology, and so we mostly leave it out of calculus classes. Okay, but what are we focused on? What we're focused on is we're focused on vector fields. So I'll light up vector fields over my head. Remember, a vector field takes as input a point in either the plane or in space, and it gives output a vector, either a plane vector or a space vector. The most common vector fields we'll deal with will have you pick a point in space and they output a vector. So that would be like the common vector fields might be the wind in the room. Like the wind in the room you're sitting in. Every point has some airflow in some direction, and each point might give you a different airflow, and that airflow both has a magnitude and a direction. So that's a vector field. The other kinds of objects we're going to be working with are functions. What kind of function are we taking the gradient of? I guess it's these kinds of functions. So if you have a function that takes as input a point and gives you a number, you can take the gradient of that function by taking all the derivatives, all the partial derivatives, and putting them in the different slots. Yeah, that's right. Okay, so a vector field is conservative, and we defined this in 17.1, but it's conservative if it's the gradient of some function. This function is phi, and we're just like really running out of f's. So it's phi in Greek, and like we wanted f for a function, but then we had f, and we usually use f for our vector fields, and we're just running out of f's, and this is the next best f that we have available. So a vector field is conservative if it's the gradient of a function. This is a huge important definition. Okay, so how do we test if something is conservative? If you happen to know that your vector field came from a function, like came from the gradient of a function, then great, like you just know it's conservative. But if I hand you a random vector field, then it's going to be hard for you to tell whether it came from a gradient. So we have a test to figure out if something came from a gradient, and it looks like this. If your vector field is FGH, and it's on a simply connected region, and they all have derivatives, then you can test whether your vector field is conservative by testing whether partial f partial y equals partial g partial x, partial f partial z equals partial h partial x, and partial g partial z equals partial h partial y. Later, we'll find out that these conditions have something to do with something called the curl of a vector field. Yeah, I won't define the curl right now, but it will turn out that these conditions come from saying that the curl of the vector field equals 0. So as we get deeper into chapter 17, we'll get to combine more and more of the facts of the class into one fact, which is going to be this fact that I've put up at the top of the screen here that I've referred to a couple of times, but we'll get back to it. Don't worry about it for now. For now, it's just if you want to tell whether a vector field is conservative, you take a whole bunch of partial derivatives of all of its things and check them to see if various ones are equal to each other. This is specific to 3 dimensions because it has all this z stuff in it. If you only have 2 dimensions, then you just only have to check the one that has x and y. Okay, so let's prove at least part of the theorem. So first we want to say if f is conservative, then all these facts are true. And that's not too hard to see. So suppose f is conservative. F being conservative means that it's the gradient of this function. And that means that it comes from the partial derivatives of this function. Then if you check these partial derivatives, partial f partial y, well, what's in the f slot is phi x. And then we're taking the y partial derivative of phi x. And partial g partial x is, well, here's g, phi y, and we're taking the x partial derivative of phi y. And we got the mixed partial derivatives of this function. Because we've demanded that the function is going to be nice and smooth, then these are just equal. The mixed partial in different orders comes out the same. So that covers the first one. And then for the other ones, like, you get the same issue. Partial f partial z is going to be phi z. Oops. F was phi x. And then partial f partial z is the z partial derivative of that. H is phi z. And the x partial derivative of that is phi zx. And this is another mixed partial. And it works for the other one too. This is yz equals zy. So if the vector field is conservative, then these things are true. We would need to prove more. We would need to prove that if these things are true, then the vector field comes from a function, so that it's like both ways. We won't prove it in this class, but like we could. It's just we don't do every single thing that we could. So let's try to do this. Let's try to use this. Here's a vector field. It's a vector field in 2 dimensions. So the question of whether this vector field is conservative is the question of whether I can find a function where this is the gradient of the function. So we're looking for a function phi from R2 to R, where my vector field is the gradient of this phi. That's what this question is asking about. To tell if something is conservative, we just use the test. The test says, try the y partial derivative of the x slot and the x partial derivative of the y slot. See if they're equal. So you do the y partial derivative of the first slot and the x partial derivative of the second slot. If they're equal, that means that the vector field is conservative. It's a little bit frustrating because we're trying to find the potential function. We're trying to find this function phi, and all this test does is it promises us that there is a function phi. It doesn't tell us what it is. So to actually find the potential function for phi, we use the plan that we used long, long ago when we first introduced partial derivatives, which was, well, if this thing is the x partial derivative, so let's find phi. If y cubed minus 2x is the partial derivative of this mysterious function, then we can find this mysterious function by integrating with respect to x. Let's see what we get. We get xy cubed minus x squared plus c. Now, this c is a little bit sketchy because we're only doing an x integral. So anything that's made of only y's would appear here as a constant. So we write c of y to say, look, here's all the x's in phi. If phi has x's, they look like this. This part of the answer doesn't tell us anything about the terms that have only y. Similarly, we can do the same thing with the second part and say, well, 3xy squared is apparently the y partial derivative of some function. So my phi is the integral of this thing with respect to y. And you have to use all of the parts of the vector field to get this. So do the y integral, we get xy cubed plus c. This c just means that there's no y's in this part. This c is a function of x. Between the two pieces, you'll be able to put together, like piece together a function phi that works. This one says all the x's are in these terms, and this one says all the y's are in these terms. So it doesn't look like we will have to have a piece that's just x's, this minus x squared, but we won't have to have a piece that's just y's. Combine these together, and phi is xy cubed minus x squared. Technically plus c, where c is like any number, but this would be a potential function for f. To check it, what you would do is you would just take the x partial derivative of this and make sure that it matched, and take the y partial derivative of this and make sure that it matched what came out of f. By doing that, you check that the gradient of phi is f. Nice. Man, we're really dancing around the physics implications here, but whatever. We'll just do the math for now, and we'll talk about physics later. So here's a three-dimensional vector field. So now, instead of looking for a function of 2 variables, now we're looking for a function of 3 variables. We're trying to find, does capital F equal the gradient of some function where the function takes 3 variables as input? Well, let's do the test. The test says that you're supposed to match up a whole bunch of different partial derivatives and make sure that they all equal each other. The first one is to check that the x slot with respect to the y variable comes out the same as doing the y slot with respect to x. Well, what is partial f partial y? That's 1. Partial g partial x is also 1, so that works. So you kind of do like the x slot with respect to y and the y slot with respect to x. That checks the xy and yx matched up. Then you can do xz and zx. Well, partial f partial z is 1. Partial h partial x is also 1, so these match. And then finally, we can do y and z. So we'll do yz and zy. Partial g partial z is, they're all 1. All 3 of these matched, so that means that our function phi exists. My vector field is conservative. Essentially, there's some quantity that is conserved when you move through this field. What is it? Well, you have to go find it. And you find it like piece by piece. To find phi, you take the x integral of the x slot, because supposedly there's this function where the gradient of phi equals all this. So supposedly phi x is y plus z. Supposedly phi y is x plus z. And supposedly phi z is x plus y. We are guaranteed that the function exists. We just have to find it. So if you look in the x slot, you can figure out what's going on by integrating with respect to x. If you look in the y slot, you can find what's going on by integrating with respect to y. And if you look in the z slot, you can integrate with respect to z. And these answers will all be different, but you'll be able to find the pieces that overlap, and they will agree. So let's do the x integral. I get xy plus xz. And then there's a constant, and the constant, it could have y's or z's in it. So any term with x has to be xy and xz. In the second slot, when I do this integral, I say, oh, well, I need an xy and I need a yz. And then there might be some stuff that doesn't have any y's in it. And then in the third slot, I have that phi is xz plus yz, plus maybe some stuff that doesn't have z's. In total, the 3 components all combine together to tell us, yeah, you need an xy, you need an xz, and you need a yz. And this potential function will work. Technically, you could also do plus 10, and it would still work, because these c's could all equal 10. But you look at the 3 outcomes and make sure that your answer corresponds to all of the answers. It's not like you add the answers together. So yeah, this function, if I take its gradient, I get f, which means f is a conservative vector field, and this phi is its potential function. Nice. Wait, what does that say? Ooh, apparently there's something on page 117 of your book. Okay, let's deal with some of the implications of what conservative vector fields are good for. So here's a vector field. This vector field, I can tell that it's conservative because I can do the test in my head. I do the y partial derivative of the x slot and the x partial derivative of the y slot. And when I do that, I get 0 for both. Since those partial derivatives match, I know that this is conservative. So this is conservative. The potential function is, well, it has to have an x squared to go with 2x, and it has to have a half y squared to go with our y. So this is our potential function. That's not the question. That's just like something that you can kind of get used to. Once you start seeing a vector field, you can go, well, you know what would be really nice is if this vector field was conservative, because then I would have a potential function and I would get to use the idea of potential energy from physics to do my problems. You don't have to do that yet, but that's the point of this section. So we're going to take this force field and then we're going to move along this path. The points are a little hard to see, but this is a line that goes up to 2, 1 and starts at 0, 0. Find the work done by the force field. Work is the integral of f dot dr. And if you can figure out what these objects are, then you won't have to look up what's going on. Like what is f and what is dr? What are these things? Well, r is a parametrization of the path. So let's parameterize it. R of t is, this is a line segment. So I'll use the line segment trick, which is I'll have a starting point, 0, and then I go over 2, up 1. So I'll do plus 2t and plus 1t. And the bounds here will be t goes from 0 to 1. Once you've written down a parametrization, that lets you turn the integral into a t integral. The t bounds go from 0 to 1. My vector field is 2x, y, and dr is the derivative of this, dt. You notice that oh crap, I have x and y in my t integral, but this is x and this is y. So x is 2t and y is t. Now I have all t's, so I can do the dot product and then do the integral. The dot product here is 8t plus t. So I get 9t. The integral of that is 9 halves t squared. So the total work done is 9 halves. That means that this vector field, which is exploding outward from the origin, actually helps us go along this path. It's it's doing work to help us move that way, because I got a positive answer. Yeah, okay. We'll use the same vector field on a different path. This one is not a line segment, so when I parameterize it, I'll use the trick that I use when I have a function of x, which is I'll let x equal t and y equal, well, oh, it just tells me the parameterization. Okay. Is that what it did for the previous example and I just made my own? Oh, I did, yeah, okay. So you could use this parameterization also and you would get the same answer. I parameterized the line segment a little bit differently. I just walked along this line segment at double speed compared to what this parameterization was telling us. Okay, so here's C2. What's the work? This is a different path, but it ends in the same place. It starts at 0, 0, and it still gets us to the point 2, 1. Now, in a situation where there's like wind blowing around you, you might get a different amount of work done. If you like go around the hurricane, then the wind won't blow on you as much. So like going a different path to the same destination might be a good idea. Let's see what happens here for this vector field. The work is the integral of f dot dr over the curve. We're changing everything into a t integral. dr is the derivative of r times dt. So dr is 1 half t dt. And f is the vector field that's up at the top of the page, which is 2x comma y. Now x and y, we don't want x and y around in our t integral. So I go look up what x and y are. Here's x in our parametrization, and here's y. So I've got t, a fourth t squared, dotted with 1 and half t dt. Let's do the dot product, and then we can do the integral. So t times 1 plus a fourth t squared times a half t, wow, an eighth t cubed. All that integrated dt. That's half t squared plus a 32nd t to the fourth from 0 to 2. Okay, so I will have, oh wait, hang on, I messed something up. It was supposed to be 2x, and I just put x here. So I need another 2 here. And that puts a 2 here. And that 2 cancels with this half. Okay, then we plug in 2. I get 2 squared plus 16 over 32. And so I still get, I got 9 halves. 9 halves was the same answer to the first question. So what happened so far is we have a vector field. It happens to be conservative. We took 2 different paths to the same endpoint, and the work done was the same. We doing another one? Awesome. Here's a different path. We'll go up and to the right this time. We're still headed for the point 2, 1 from the point 0, 0. Different parametrization, no big deal. R of t is t square root of t over 2. T goes from 0 to 2. The work is the integral of f dot dr. dr, I know what dr is. dr is the derivative of r times dt. So I'll have 1, and then, 1 over 2 square root of t over 2 all times a half. dt. And then f is 2x y. Our integral is now a t integral, so it should get t bounds. The bounds go from 0 to 2. Again, x and y sitting here, and I don't want x and y in my t integral, so I substitute in what x and y equal. When I do the dot product, these gross square roots cancel out, and the thing I actually have to integrate is 2t plus a fourth from 0 to 2. Well, that's t squared plus a fourth t. I don't like this answer. From 0 to 2. Oh no, it works out. And that's 4 plus a half. So I get 9 halves. This is not a coincidence. We did not carefully choose these paths. What this tells you is that for this vector field, and it's not true for all vector fields, you know that if there's a strong windstorm in an area, you can avoid getting the wind blown in your face by just walking around it. So it's not true for all vector fields, but for this vector field, the path you take does not affect the work that's done. So the work is independent of the path. As long as we started and ended at the same points, it didn't matter which way we went. We ended up getting the same amount of help from the vector field. that should sound familiar. There's a common force that happens to you that it works the same way. It's gravity. If I take an object and I am headed from this height to this height, it doesn't matter what path I take. If I go like this, or if I go like this, gravity does the same net amount of work on me no matter which path I take. So that fact ends up being really powerful. It's the fact that lets you use the potential energy formula in physics. So this is the fundamental theorem for line integrals. It says that if you have a conservative vector field, namely you know the potential function, then you can do line integrals without actually doing the integral. Okay, but no, that was a terrible way to phrase that. That you can do line integrals using the potential function. So let's see how this works. So it says, suppose you have a region and you've got a potential function. Suppose you have a curve that's like going around in the region and it's parametrized this way. And you have a start point and an end point. So here's the start and here's the end. Okay, what's the plan here? Where's f? Oh, this is the potential function. So f is the gradient of the potential function. So it's phi x, phi y, phi z. And then the work done by this vector field when we go along this path r is the integral of f dot dr. And I have all this stuff written down, so I can say f is this thing. Dot with dr. And I'm going from A to B. So what are these? Well, if I dot all these together, I get oh, I see what's going on. Sorry. What do I get if I dot these together? I get partial phi partial x times dx dt plus partial phi partial y times dy dt. We're doing this live here. Plus partial z partial t, oops, not t, z times dz dt. All this dt. So I literally just dotted these together and wrote it in a different, more suggestive way. What am I suggesting here? This should look familiar from like a couple months ago, which is say you have a function that depends on x, y, and z. And those x's, y's, and z's all depend on t. Then if you wanted to find the derivative of phi with respect to t, what you would do is you would take all the paths to t through this little diagram and add them up. And that's what this is. So what you see here is that this is the chain rule result of this outcome, of like this relationship of variables. So the chain rule tells us that actually what happens when we find the work done is that we're finding the integral of d phi dt. And if you take the integral of a derivative of a function, you just get the function. This is the fundamental theorem of calculus, evaluated at the bounds. So you get phi of b minus phi of a. Okay, I stumbled through that, but whatever, we got there. The point is, if you have a conservative vector field, so you know its potential function, and you're going through to find the work done by that vector field, it ends up that the only thing that matters is the value of the potential function at the end and the value of the potential function at the beginning. And this is just because of how the chain rule worked. This proof is actually really cool. I wish I had done it better. Well, I don't have time to record it a second time. So, we used the fundamental theorem of calculus, so we shouldn't be surprised that the end result looks like the fundamental theorem of calculus again. But here it is. If you have a vector field that is conservative, then the work done by the vector field on a curve is just the difference of the potentials at the 2 points. A and points, so here the points are capital B and capital A, so let's do it like this. Yeah, so this is the fundamental theorem for line integrals. Notice that this only works if you can find a potential function. So it's kind of the same deal as how the original fundamental theorem of calculus worked. It's great if you can find an antiderivative. And this phi, this potential function, is kind of like an antiderivative for a vector field, except it's like an anti-gradient instead of an antiderivative. But it works the same way. If you can find the potential function, then the integral of the vector field is you just use the potential function. Hopefully we get to go back to that last example. Oh, so why did we get the same answer for each of those work calculations? It was because in that page where we did 3 calculations, f was conservative. In particular, I think f was 2x comma y. And so its potential function was x squared plus half y squared. And every time that we took a path from 0, 0 to 2, 1, all we did is we actually found the difference in potential between those 2 points. Let's do it. So you plug in 2, 1 into the potential function. When you plug in 2, 1, you get 4.5. And when you plug in 0, 0, you get 0. That's great. Okay, so if a vector field is conservative, the work done by the vector field is independent of path. It's dependent only on the endpoints, only where you start and end. This is a huge fact. This is a big accomplishment of vector calculus, is that you can figure out the work done by some vector fields just using a potential function. So let's do a problem that would have been hard and is now not hard. So this says find a line integral, and you go, okay, I'm gonna have to parametrize the curve, take the derivative of the curve, plug it all in, do a dot product. But then you notice that it tells you the vector field, and it doesn't tell you what the curve is. So you can't even parametrize it. That's a clue that wait a minute, maybe f is conservative. And in fact, we found earlier that this one is conservative. F is the gradient of phi, where phi is, what was it? I guess xy cubed minus x squared. So this vector field is conservative, which means all the information we needed was the start point and the end point. And we can just find the work done by finding the potential at the end point and finding the potential at the start point and subtracting. So you plug in 3, minus 1. And plug in 1, 5. Looks right, maybe. Yep. And I get minus 12 minus 124. So the work done is minus 136. If you wanted to, you could draw a line segment between those 2 points, parameterize the line segment, do the whole dot product thing and you'd get the same answer. But the point of the fundamental theorem of line integrals is that you can just do the integral using the potential function. So this equal sign here is the fundamental theorem of line integrals. I don't know at this point in the class if you're gonna like just be tired and want it to be over, or if you're gonna see that this is awesome. It's awesome. Okay, question, what if we changed the orientation? What if we switched the start and end point? If we switched the start and end point, then instead of the vector field working against us, the vector field would help us. So then we would get that the work is positive 136 instead. And you can see that by just saying, oh, well, if I switched these two, I would do the difference in the opposite order, so I'd get the opposite answer. Okay, so here's our theorem. Our theorem is that the work done by a vector field is independent of path, and that happens if and only if f is conservative. So if the work done by your field happens to be independent of path, then you know there's a potential function out there. And if you have a potential function, then the work done is independent of path. This is great. It's kind of like the summary of what we've done here. I'm not proving that. Not in this class. You can take classes where that will be proved. They won't be 200 level. Okay, let's do a couple of let's do like a line integral kind of like summary of all the different ways we have to do the line integral. So here's a vector field, and here's a path. The path says go from 0, 1 to 1, 0 along the unit circle. So let's just do it one way. The first time, let's just do the line integral without thinking of the fact that this vector field might be conservative, and so we might be able to escape everything. So if we just do this directly, we would say, okay, I'm going from 0, 1 to 1, 0 along the unit circle. This is my curve C. I can parameterize it by r of t is, well, I don't want cosine theta comma sine theta, because then I'll go counterclockwise. So how does it work? If I just switch them, does it work? Sine theta, cosine theta? Now at theta equals 0, I get 0, 1. And at theta equals pi over 2, I get 1, 0. Yeah, so this works. Theta here goes from 0 to pi over 2. So here's my parametrization. Then the work done is the integral of f dot dr. F is all this stuff, and the x's and y's come from my parametrization. So I'm going to integrate y cubed minus 2x, 3xy squared. So here's f, and then I'm going to dot it with dr. dr is the derivative of this, dt. My bounds, I'm now a t integral, so I want t bounds. Am I going to be able to do this integral? I don't know. Let's see. So I'll do the dot product. I get, oh, I don't think we're doing this integral. Cosine to the 4th theta minus 2 sine theta cosine theta minus 3 sine squared theta cosine squared theta. Wait, dt? What am I talking about? Yeah, this is d theta. I must have said something really, really wrong earlier, because I must have said because it's a t integral, we use theta bounds, but it should be, because it's a theta integral, we use theta bounds. Okay, I'm not doing this integral by hand. This is insane. I guess the point of this is, like, if you actually do it directly, you get a ridiculous integral. So this is sad times, but I think we could probably just ask a computer to do it for us. Let's do that. So I'll go to Wolfram Alpha. I want the integral from 0 to pi over 2 of cosine to the 4th x. I'll just call them all x so that it's easier to type into Wolfram Alpha. Cosine to the fourth minus 2 sine cosine minus 3 sine squared cosine squared. If it can even read what I'm talking about here. Cosine to the fourth minus 2 sine x cosine x minus... It looks like it parsed it correctly and it got minus 1 as my answer. So this is the... This is a very non-satisfying answer, at least to me. It's like, hey, I did it, I did the setup, and then I gave up and I had somebody else do it for me. So I don't like this. But this is one way to find the work done by this vector field when we move along this path. The other way to do this would be to say, wait, this vector field might be conservative, and so I might be able to get out of doing any work. Is this the same vector field again? Yes, we found this. We found the potential function like several times now. It's xy cubed minus x squared. Once you realize that the vector field is conservative, you could use this to say, oh, it doesn't matter which path I take. I'll take an easier path. So instead of having all these cosines and sines, which made my problem really difficult, instead I'll just say I'll start at 0, 1 and go to 1, 0 by a straight line. Just use a line segment. Since it's a line segment, I can use my trick where I start at 0, 1, and I go, my x goes up 1, and my y goes down 1. And then my work is the integral of f dot dr over the curve C. F is this thing with all the cubes and stuff. So f has y cubed minus 2x. Here's y cubed minus 2x. And then 3x y squared dot dr. And my t bounds here, because I've done a line segment, are from 0 to 1. This integral will be much easier. Like I can do this dot product. And we could do this, and I feel like we have better things to do. But this one would actually be possible, and you'd still get the same answer. And finally, the grand victory solution is to say, wait a minute, don't do any line integrals. When you have a conservative vector field, that means you have a potential function. And you can just use the potential function. The work done by the field is the difference of the potentials at the 2 points. You do the end point minus the start point. So when you have a conservative vector field, this is how you should find the work. Plug in 1, 0, and you get minus 1. Plug in 0, 1, and you get 0. So use the fundamental theorem of line integrals when you can. If your vector field is conservative, then go for it. If your vector field is not conservative, then you have to just directly do the line integral. And it's not that bad. It's just sometimes the integrals can come out bad. Nice. Okay, one more thing before we write down a bunch of facts, like the official summaries. If you went all the way around the unit circle, then the work would be 0. And the reason is that if your start point and your end point are the same, then your work will be the potential at the end point minus the potential of the start point. And if the end point and the start point are the same, then these cancel and you get 0. So if you ever use a closed curve, and you would do that by putting a nice little circle on the integral sign to make it look like a fancy line integral. If you do the integral around a closed curve of f dot dr for a conservative vector field, you get 0. That turns out to be another condition you can use to tell if a vector field is conservative. If the line integral of around every closed curve, this circle means closed curve, is 0, then the vector field is conservative. Okay, so all of these things, these are all equivalent ways to say that a vector field is conservative. You could either say, look, I found the potential function. I know it's conservative. Or you could say, well, this work integral is independent of path. Or you could say, all the closed paths have 0 net work done. Any of those is enough. They're all equivalent facts. They're all the same thing. So these are equivalent conditions to show that something is conservative. In physics, when you have a force and you realize that the path doesn't matter and the force does the same work no matter which path you take, that's when you realize that there's a potential function.